I just heard a beep. Okay, so maybe it started. All right. So this is what your graph should look like if you collected reasonably accurate data in graphical analysis. If you had some issues with getting this to display correctly, maybe you didn't create a second data set, or maybe you didn't label things correctly. I have noticed some folks not putting a unit of measure. So like when you get in here to column options and you change the name of the variable on the axis, you are still supposed to put a unit of measure in here. I had noticed when I walked around, some of you didn't change the name, didn't put units of measure in. You kind of need to do all of that so that your graph here displays the variables like mass on the y-axis and volume on the x-axis. Hopefully you can make sure that that's done. And then I also click up here to rename the data set so that I know which one is my PVC set. And then again, adding a new data set. That's what we did in class by clicking on here, adding new data set. And that gave us a brand new one next to our the first data set. And then you could go in here and change this name, and I renamed that to aluminum instead of data set 2. So that is kind of the process we went through in class. And then over here, well, hopefully you remember to get down here and do the edit graph options. Always show 0, always show 0, so that we have our origin down here. That was kind of important. And then the other thing that we did is taking the mass here and making sure that you have both of these clicked on. If neither of these is clicked on, then you will see no data in here. And then as you click one on, you'll see a data set. And as you click another one on, you'll see a data set. And of course, because I did that, I lost my best fit. So both those have to be toggled on. And then I got to go back down here and apply curve fit, and it will suggest linear, and I will say yes. And so we have it like this. Now, in your comp book, you were supposed to sketch some things for this class, for actually today, for the B1 folks. For the B2 folks, it'd be for Monday, and of course you'll see this video then. Now, the M in our little box here, those are slopes. Like M is the letter, the symbol we use for slope in math class, and so that's the slope of each line. You didn't have to calculate it. Graphical analysis did it for you. So what you need to do in your comp book is sketch this graph the way it looks. Don't have to plot points. You don't have to put numbers on it, but you do have to write down the variable names on both axes with units of measure and sketch 2 lines on there that look like what these look like, and then list the slopes, and then figure out the unit of measure for the slope, and then write a sentence for that slope of what it means. So that's what you were supposed to have done for today. So what I'll do then is I'll head over to whatever this thing's called. I don't even know anymore. Smart notebook. Okay, so let me get this going. Hopefully this will work. Of course. Let's try it again. Black line, fine line, and that's orange. That is not what I picked. Oh my gosh. You saw that I picked black ink, and it still has orange picked. Let's try this again. There we go. All right, so again, here's your graph. We had volume down here in centimeters cubed. We had mass up here in grams. And then I'm going to go ahead and use colors because I can. Let's see, my blue one was, oh my gosh, was my blue one aluminum? Yes. My blue one was aluminum, and then my red one was PVC, like that, I think. Oh my gosh, now I got to go look. Yes, that's right. So this one is PVC. Again, label them so that you can see which ones are which. The whole point of this, folks, the whole point of you doing this is so that when in the future we have to refer back to this, you have it all in there. You have a record written down of what you did in class, what data you got, what your graph looked like, what's where, and then of course you're going to put the slopes now on each of these lines next to it, and then write a sentence of what each of those slopes mean, so that, again, we have a written record of what we did in your comp book with everything else that we have. So we don't have to pull up graphical analysis anytime we have a question about it. So my slopes were, if I remember correctly, 1.362, I believe. And then my aluminum was 3.007. Now, I guess I'll leave it in blue. Part of the question here that you have to figure out is, what is the unit of measure on the slope? The unit of measure on the slope. Now, remember, how do you find slope? Now, I know you didn't have to find slope on this. Graphical analysis did it for you. But if you did have to find slope, you take the rise over the run. That would be a mass over a volume, right? So you would have, again, you would have a rise over run. That would be your slope, which, again, is a mass over a volume, which is a gram over a centimeter cubed. Like that's how you would explain this. A rise over a run, or a mass over a volume, or a gram over a centimeter cubed. That's what we're doing. So that means these numbers here, they are grams / centimeters cubed. Grams / centimeter cubed. Again, we don't write it necessarily like this right here as an actual like top and bottom fraction. We just slash it like that. And so then the PVC is grams / centimeters cubed. Now, at this point, we need to be able to figure out how to write a sentence that describes what these mean. All of the sentences that we've written for slopes have had the same form. They are so many, like there are so many of these for every one of these. Yes? That's what we've done. So this many of these for every one of these. So how do you actually write that out? Well, like this. So for aluminum, I should move these a little bit. Hold on. Let me move that down here. Let me move this over here. Move this down here a little bit. Need a little bit of space. So if I'm describing aluminum, I would say there are 3.007 grams of aluminum for every 1 centimeter cubed. So that's what it's telling us, that there's 3.007 grams of aluminum for every 1 centimeter cubed, which means for PVC, I'm saying that there are 1.362 grams of PVC for every, 1 cm cubed. Hopefully that makes sense. They all are set up the same structure. Now, what exactly does this mean? What is this telling us about PVC versus aluminum? Well, before we even answer that question, if you remember back to when I was talking about this for the first time, the question was, what is the relationship between mass and volume? What is the relationship between mass and volume? Well, it wasn't even, is there a relationship between mass and volume? Because by looking at the graph here, is there a relationship between mass and volume? Yes. There is a relationship between mass and volume. Because one of these, like the volume getting bigger, means the mass gets bigger, And so one of them changes and then the other one changes also. So that means there is a relationship. The bigger piece of aluminum has more mass. The bigger piece of PVC has more mass. The smaller piece has less mass. So again, they are dependent upon each other. All right. Now, the next question is this. If I have two blocks, one of aluminum, one of PVC, what does it mean? Like what are these numbers telling me about those two little chunks? Like for instance, if I do this, if I sketch let's just pretend that this is a 1 centimeter by 1 centimeter by 1 centimeter block. And that's of PVC. And then I have another one of, I should have just copied that other one. Oh no. I have another one of, that's 1 centimeter by 1 centimeter by 1 centimeter. And so I have aluminum here, and I have PVC here. What are those numbers telling me? The numbers that we have for slope right here, what's it telling me about this chunk of aluminum versus this chunk of PVC? Again, that's 1 centimeter cubed. This is 1 centimeter cubed. And so what are our slopes telling us? It's telling us, at least for my numbers, that aluminum has a mass of what? That chunk of aluminum has a mass of, oh, of course it's red. I don't even care. 0.007 grams is what that mass is. And this one is 1.362 grams that this chunk is. Same size pieces, they don't have the same mass. Now, what does that mean? What is that telling us about those chunks? How can you have the same size piece, like these little things right here, this is a centimeter cubed. So if we had two of these, one of them being aluminum and one of them being PVC, they don't have the same mass, which means they don't have the same amount of stuff, which means they don't have the same number of particles. What is that telling you about the particles in the aluminum chunk, the little block of aluminum? How are its particles different than the PVC's particles? Think about that. If you look at the numbers here, there's more than twice the mass, according to my data, there's more than twice the mass in this block of aluminum than there is in this block of PVC, which means there's more than twice the particles. There's more particles here than there are here, which means they have to be what? Again, more particles in the same size space than over here, which means the particles have to be closer together. To fit that much more mass in the same space, the particles have to be, and a word that was brought up, compacted. The particles have to be tighter, more tightly packed. That has a name. Do you know what the name of that is? So how tightly packed the particles are in something, that has a name. Do you know what it's called? I hope you're thinking it. You've learned it before. I know you've learned it before, but you may have forgotten. I don't know. It's called, I'll just write it. It's called density. So density, the measure, oh boy, the measure of how tightly packed the particles are. Oh no, this may be right about where my head is in the picture. In a substance. I'll have to scroll up. Oh no, I can't. Oh no. Hold on. Oh boy. I'll get it. Extend page. Whew. Oh my gosh, that could have been disastrous. That could have. Now I have to do this. Now I have to make a little mark down here. That way it won't. Oh, okay. So that should be above where my head is now. So again, density, the definition, the concept definition is the measure of how tightly packed the particles are in a substance. And so these numbers right here, these numbers are density. The slope of this graph is density. And so aluminum, based on my numbers, is like twice the density of PVC. More than twice, actually, based on my numbers. Now, I want you to look at first period's numbers. I know not all of you are in first period. Some of you obviously are in different class periods. But this is the spreadsheet we had for first period. And I don't know why some of these are going in superscripts and some of these are going in just caret, but whatever. So if you look at these, except for groups 1 and 2, these are all really close to the same. We all are like 1.3 something, like upper 1.3s, and then 1.43. So very close to 1.373839, somewhere in that range. Now, everybody with aluminum, with the exception of me, I guess the 2.89 is up there a little bit closer to 3, but in a 2.6 something range or 2.7. So very close to 2.6 something, upper 2.6s, I guess. And then there's me. So everybody measured these things a little differently. And my sets, the sets of my cylinders, they were bigger than the sets that you all were even using in class here. And yet my PVC number here is very similar to yours. So these densities, that's what they are, okay? These numbers are telling us how tightly packed these particles are in these substances. Now I want you to look at this. How do you find the slope? It's the mass over the volume. It is the mass to volume ratio. This here is a ratio. That's a ratio. And it's the ratio of mass to volume. So that's the mathematical definition of density. Here is the concept. So it's talking about how tightly packed the particles are. More tightly packed means more dense. Less tightly packed means less dense. And the measure, the number that tells us that is this mass to volume ratio, which is density. So the mathematical definition of density is mass to volume ratio. It's telling us how many grams there are for every unit of volume. And so again, if you look at these numbers right here, a 1.3 something, 1.4 something, and then we have a 2.6 something, this is twice that one, double this one. So aluminum is way more dense than PVC. In other words, those particles in aluminum are packed in a whole lot tighter. Now, what I did, something else I did in class that you wouldn't have been here to see, is I took some of the pieces of aluminum that we used and I put them on, oh boy, some of the pieces of aluminum and PVC. Oh, sheesh. Oh, before I even did that, I did this. I took a piece of, I have these sets here. This is PVC and this is aluminum. I put both of these on a balance, a 2-pan balance, that when you have equal masses on it, they balance out perfectly. These two pieces right here, they balance out perfectly. And I want you to look at how their sizes compare. Same diameter, but the aluminum is like half the size, half the height of the PVC, but it's the same amount of stuff, which means that the aluminum's particles have to be smashed way closer together than the particles that are in PVC. Or you could think of it that the PVC particles, they're really spread out compared to the particles of aluminum. And so then I asked, okay, in a particle diagram, How do you show that? Like, how could you show that in a particle diagram? Well, maybe like this. Maybe you would draw an aluminum cylinder. Oh, I should make it. Oh, sheesh. I should make it smaller. I'll do it over here. Oh, no, you idiot. So if this is the little cylinder of aluminum, and this is the cylinder of PVC that I'm holding, again, like twice the size, and that's PVC. How do I draw my particles in there to represent how these might look inside? Because again, we have to imagine it because we can't see the particles. So this is the abstract part that I had talked about before. Some people are okay with that in the chemistry part because you can't actually see the particles, but so you have to imagine how they're arranged inside this stuff. And so let's just say for aluminum, well, I'll just start drawing some particles. I don't know how many I'll fit in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 particles. So I have 18 particles inside the aluminum cylinder. How many particles are in the PVC cylinder? Well, what did I tell you happened on the scale? When I put these on the scale, they balanced perfectly. They were completely balanced, meaning they have exactly the same mass. And if they have the same mass, that means they have the same number of what? Particles. So, how do I draw 18 particles in this thing? How do I draw 18 particles in that? Well, I just start drawing. But they're going to be what? Hopefully you're thinking, what? Oh, that thing got erased. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, oh boy, 17, 18. These particles are way more what? Spread out than these particles, which makes PVC less what? Dense. They're not nearly as packed as the aluminum particles. Aluminum particles are packed in there tight, and that means it's dense. These are spread out. That means it's not very dense. And we can see that in our particle diagrams when we sketch them to describe the fact that they have the same mass because they both have 18 particles, but one's particles are way more spread out than the other. Now, here's what you can't do, okay? You can't, and this is a very common thing that people will say, is that aluminum is heavier than PVC. And you'll look at this, and look at that. Aluminum is way heavier than PVC. You can't say that because a really tiny piece of aluminum is not heavier than a big piece of PVC. It's not about who's heavier and who's lighter. It's about who has more mass in the same amount of space. And so we don't talk about what's heavier and what's lighter. We talk about what's more dense and what's less dense. So you have to use the term dense or density to describe the differences in these substances. It's about how tightly packed the particles are, not how heavy or light something is. Okay? So if something is more dense than something else, you don't say it's heavier, you say it's more dense. There's more mass per unit volume. For every cubic centimeter, there's more mass for aluminum. But you could have a piece of aluminum, like for instance, what do you think would happen if we were to take, what do you think would happen if I were to take the smallest piece of aluminum and one of the big pieces of PVC and I put them on the scale? It's going to tip toward the PVC side because this has more mass than this one. Okay? So aluminum doesn't always have more mass. Aluminum is not heavier than PVC. These two pieces, the PVC piece is heavier. So you can't talk about which substance is heavier or lighter. You have to talk about the substances in terms of density. I hope that makes sense. Now, there is an assignment on Classroom that I gave at the end of this class period. So the stuff that I just was talking about, all of this stuff here, there is an assignment on Classroom that you will have to do. only the first 2 pages. So read the instructions. Okay. In fact, I can even go there and show what the assignment looks like. Hopefully. Classwork, unit, yes, this one here. So this is what the assignment looks like. Do not recreate and redraw all of this stuff. That would be a total waste of time. What you need to make sure in your comp book, you are answering these questions. Again, read the instructions and do what it says. You will have a greater than, less than, or equal to sign comparing the mass, volume, and densities of blocks A and B. And then you'll give a reason, just a brief sentence or statement explaining how it is like if you say the mass of one is different or the same as the other one, then you have to give a reasoning. Well, how did you know that? That's what that part is. And then there's more of that down here, only instead of just 2 comparisons, we have an A, a B, and a C to compare. So you got a few more of those. So again, this shouldn't take very much space in your comp book. And again, you're going to have a bunch of greater than, less than, or equal to signs, but then just a little statement for each of those as well, describing how you know. And then page 2, there's numbers 3 and 4 here, and 4 has a couple different sections that you'll have to answer in that. But that is it. Now there is a page 3 and a page 4. I don't care about those yet. We'll get to that. But for Tuesday or Wednesday, depending on which block you're in, that's when this will be due. So I hope that makes sense, and I hope that that you kind of get and understand this whole concept of density. So we've talked about mass being how many particles there are or how much stuff something's made of. We've talked about volume, which is how much space something takes up. And now we're talking about density, which is looking at both mass and volume at the same time. This mass to volume ratio, which again is giving us an idea of how tightly packed the particles are together. And this is a property of matter, all right? Now, the thing about it is, if I take this aluminum cylinder right here and I start bashing it with a hammer, it's going to start to deform and change its shape. But I can't make the particles any closer together. In fact, if I start hitting this thing with a hammer like this, it might actually start to squish. And as it gets shorter, what's probably going to happen? It's going to start getting fatter because I can't make the particles get any closer together than they are. Aluminum's particles are spaced in a way that there's always 2.7. Oh, I didn't even tell you that. Oh my gosh, I didn't actually tell you what the densities should be. Gosh. So for PVC, it should be about 1.4. About 1.4 grams, approximately 1.4 grams for every centimeter cubed. And so I was close. Most of you were probably close. For aluminum, it's actually 2.7 grams for every centimeter cubed. Now, I was off a little bit. Most of you were probably a little bit closer than I was. So this is what the density of aluminum should be. This is what the density of PVC should be based on really, really, really good, clean data. Now, some of you didn't have, and again, this is still first period's data. So those, if you average those out, that's really close to 2.7. I was the one that was really far off there. I don't know what happened to me. Here, groups 1 and 2 were way off, but then the rest of us all in that 1.3, upper 1.3 somethings range, except for the 1.436 here. So that's good. That's good stuff. All right, I know this was a long video, but I had to try to fit a bunch of stuff all in here at the same time. So anyway, hopefully I didn't put you to sleep and you can make sense of all of this stuff. So take care if you're at home and not here. If you were here and you just needed to go back and look and review some things, well then, yeah, I guess I'll see you later soon. Bye.